Hi folks, welcome to another episode or another viewing of our Cloud Basics channel. We're going to talk today about containers and container technology as a part of that environment and that solution. And to that end, I've prepared some slides that we're going to go through, specifically looking at the rise of the container and the container, but the way that then accelerates our operationals, ops dev, operational development sort of services and capabilities. So I always like to sort of start a quick review of who we are and what it is that we're doing here. So I'm the CTO and founder of Cumulus Technologies, which is a systems consultancy. We've been around operating in this space since 2012. I'm really looking at a couple things. One is, how do you actually scale out OpenStack? How do you make these services things that are viable as a part of the business process of a business and a technology process for a technology? As containers have become more and more prevalent, we've started to move in that space as well. So this is new for us and new for most folks, but we thought we could actually help people understand how to consider containers as a part of this overall cloud strategy. And again, Cumulus Technologies, we're systems consultants, and we support the migration to cloud and cloud environments. You can get a hold of me on Twitter, rstarmer, our Cumulus Tech company Twitter page is there as well, and coml.us is our webpage, so please check us out there. And you're actually probably watching this on the 5 Minutes of Cloud channel, but if not, youtube.com 5 Minutes of Cloud. We've got lots of little short segments there, but also some now of these longer segments that we're doing as we do as part of our meetup environment. So what we want to talk about today is an overview of the container services and space, a little history. Where did it come from? What's the point behind these containers and the concept behind containers? And why are we now talking about containers as sort of the answer to every and all developer requests? Instead of, I would like another VM, it's, I would like a container service, please give me something because I want to use these new tools. We also want to talk about some of the other pieces of the container world, really the infrastructure of containers, the container operating environments, because these are a little different than your normal container services and solutions, but they're just as important as the actual container pieces themselves. As we're doing that, we'll also talk about some of the gaps in what those container services and the operating environments provide today, and a way to look at potentially fulfilling some of those from an operational perspective. In other words, how are we actually going to implement these resources and solutions? And then we'll look at a way of unifying a bunch of these pieces. Again, we have a history in OpenStack, and so I'm going to be talking effectively about how OpenStack still fits in the container space and some of the interactions there. I'll try to make that a little bit more general. We'll talk about Amazon and Google Compute, for example, as well as ways of also addressing some of these same requirements. So let's dive into containers. What do we really mean? When we talk about containers, we're really talking first off about Linux containers, because, well, probably most of us only think that Linux is the only operating system out there, except maybe Windows. For the most part, people are talking about containers in the Linux services space. And while there are folks that are now talking about containers on top of a Windows operating system, or containers in the Windows service space, or potentially some of the history, things like Solaris containers, for the most part, we still are talking about Linux processes and Linux management. Really, when we talk about a container, we're talking about process level segregation. It may, in some models, actually look like a virtual machine. It might look like a full operating system sort of environment, but for the most part, the interest seems to be focused around the concept of process level segregation rather than system level segregation. There are a couple of technologies, and again, this is specifically in the Linux space, but similar sorts of capabilities exist within other operating systems. There's a concept of C groups, which are control groups within the Linux kernel that provide resource restriction, resource management. So I can limit the amount of memory, I can limit the number of file descriptors, and therefore access into specific file descriptors as a part of that C groups technology. The other piece is this concept of a namespace. In a sense, it's a similar sort of way, it's a different way of fencing off resources, and where namespaces tend to come into play are really within the network services environments, and to a certain extent the storage environments, a way of restricting access and resource visibility within that process environment is sort of where that comes from. Now, if we sort of back out a little bit, so rather than just talking about processes, how did we even get here? I like to think about it as starting sort of in the single system multi-segregation space. from the 60s and 70s, right? So it used to be that computer was a one-time run process. You would provide your job potentially at that time as a set of cards or maybe on magnetic tape. Your job would take the system over and run until the job was complete, and then it would go on and run the next job, so the next resource would use it. As systems got fast enough, it became possible to present as if there were multiple systems, so multiple users could submit jobs at what looked like the same time, and the system would actually share its resources a little bit more in a little bit more real-time sense. And that kind of segregation also led to this need to segregate processes from each other. The early systems didn't do that segregation, and while that was fine when there was a lot of control over those resources, eventually it became possible to consume all of the resources of the system and not really share with the other users in the environment. And it was that non-sharing kind of resource that, of course, led somebody else to say, well, how do I restrict your access versus my access? And maybe some of us remember from the early Unix days, not early Unix days, for me, middle Unix days, looking at process segregation, the root user versus other users. Already this segregation of resource access, effectively the first views of the namespace kind of model and how that mapped into the consumption within the space. Now, there were then some approaches to try to provide an entire wrapper around a process. And the first one that seems to hit the literature is the BSD jails concept, which was process-specific segregation. The Sun Solaris related developers saw that kind of a concept and implemented the concept of Solaris zones, and now there are actually containers that look a lot more like the Linux containers in Solaris as well. But this concept of a zone was similar. It was a way of segregating processes, providing some restriction around the resources they were able to use. So fairly powerful technology and conversation. The real push into the container space came with, as far as I can tell at least, a work between the folks at Canonical and the folks at Google. There were some Google developers that actually had started to work towards enabling specifically the C group function becoming a part of the Linux kernel. And as far as I can tell, some Canonical engineers focused on actually enabling the service management for that concept and that technology. Google also, in a similar time frame, I think a little bit after LXC became a technology, created a tool called LMCT-Fi, I think something along those lines, which is let me contain that for you. Effectively, let me take your process, your application, and bundle it into a container. So a pretty powerful tool for managing these containers and container services. So again, around 2005 or so about 10 years ago, Google and Canonical really sort of started to push containers as a model, partially because Google was starting to use the container model, this process segregation model, as a way of dealing with their massively scaled environment. Now, I will say that Google has this, many people look at Google or even Amazon or Facebook, some of the sort of the mega scale application resources that are on the cloud or on the public internet, and use them as an example of a cloud scale application environment. I actually think that's a little bit of a falsehood. These guys build massively distributed applications, but they're not really cloud applications they're cloud as a service applications, but their applications themselves are not necessarily quite the same. Now, some of the principles behind that massively distributed application deployment map into what we think of as cloud applications, or rather web scale applications, but I think there's often been a little bit of a disconnect there. But the container service is something that the Google engineers were looking at as a way of simplifying the deployment of 30 or 40 Google Mail application service components, right? So the mail front end for a particular cluster of Google Mail servers, or the DNS services, or any of the other services that Google has implemented to support their massively distributed microservice enabled services chains. But other than Google and some bleeding edge developers like the guys that were developing the LXC space, very few people actually implemented containers because the creation of a container was more complicated than the developers really found value in. And part of that was that there were no APIs to help manage those containers, so this concept of infrastructure as code or containers as code really didn't apply yet. That's been changing, and one of the first teams to really adjust that or shift this view, I think were the folks at Docker a couple of years back, where they took a lot of the ideas and concepts that the Google community had actually, the internal Google community had actually implemented, and applied that to some of the other concepts that have been floating around and said, well, what if we change how we deal with the container image, basically the thing that is your process bundle. So really, Docker started looking at the application and managing the deployment and service creation at the application level. So this layered approach, this lightweight approach to managing the container really shifted how the service was functioning. So that was the first thing. And so their model was to use a description of the resources that needed to be added to some kind of a base process. And in some cases, there are base processes which look a lot like the base operating system. So they have bash shell enabled. They have most of the services that you would expect running within a container environment. But often those containers are missing things like an SSH daemon, so you can't necessarily log into that container against that bash process in the same way that you might have in a virtual machine. But those light images can get even lighter, because you could just say, well, look, I'm building an application that needs Python bindings and Python libraries, so let me make sure I have just all the base libraries and components that I need to implement a Python application in this container, rather than the full operating system. And so those containers get smaller and smaller and smaller. There are also folks that are going the other direction, where they're saying, well, no, I need all of the tools I would normally have within a virtual machine, but within that process container. But the real Docker value was more along the lines of this ultra lightweight container, just enough of the resources to actually enable the application. The other thing that Docker enabled that I think further accelerated this entire process was an online registry. So suddenly you could create a container model of a very lightweight process like an Apache service or Nginx service, and push it into a registry, both for your own use, but you could also expose that registry information to the public at large. So suddenly people were sharing things like a basic WordPress-based container, or an Apache container that was running Passenger, Fusion Passenger, so that you could run a Ruby application within that container just by adding effectively your application to it. That was some of the major change that really drove the container services space. And as we look at the modern container environment, LXC has now been enhanced with LXD, which is a RESTful API on top of the LXC constructs. LXC also now has its own image repository / registry, and you can of course create your own on top of that. So the same sorts of capabilities that I think really helped Docker expand have now been implemented in other container environments. As a matter of fact, now the container community seems to be converging on some standard-based image models, some standard-based registry kinds of concepts, and I think that's good for sort of all involved. And so we're seeing that with the Open Container project, trying to drive more consistency across all of the different container engines and platforms. But really, why don't we just stick with virtual machines? I mean, if we sort of look at the three different layers of this sort of an environment, we have a physical machine. The real issue there is the complexity of getting an operating system and then an application deployed, especially if I want to do this in a rapidly deployed, rapidly changing sort of environment. Like I'd like to deploy an operating system and an application and then delete it, and then deploy it and delete it. We also have the hypervisor model, which basically says, well, we'll take a piece of hardware and deploy some form of base operating system or just hypervisor, depending on the exact capability. And that hypervisor layer will provide an abstraction on which I can then run multiple operating systems. Now, those operating systems can usually be just about anything that runs on an x86 platform. And yet still, we've seen for the most part, people are converging now towards KVM as the hypervisor extension to a base Linux operating system, providing virtualization of that hardware for a full operating system on top. So a full Ubuntu or CentOS or Windows, etc. operating system running on top of that, on top of which you layer your applications. With the container concept, we still have a host operating system. In our case, again, we're really talking mostly about the Linux-based container environment. So it's going to be a Linux-based environment, and that seems to be either Debian-driven or the Red Hat family of containers seem to be the principal ones, not to exclude RSUSE and other friends, but those seem to be the two that at least I have run into most commonly. That container engine model then has a container manager. So that would be something like an LXC or a Docker or some of the others within that space. runC is another container management engine. And that container engine is really just helping to manipulate and manage the C groups, namespaces, potentially network services interactions between the application and its libraries and the actual host operating system, because the host operating system and its hardware and network services and storage services are still a part of the picture. But that's kind of the segregation. And so when we look at that segregation, you have bare metal hardware, you have virtualized hardware is another way of sort of thinking of the virtual machine space, and then you have this container model. One of the big deltas between any one of those three processes is the time it takes to actually start a process. So from the perspective of speed, we're talking sub-second speed, basically the time it takes to start a Linux process. Yes, there's some initial configuration. I have to pass some additional parameters to the kernel to tell it how to restrict the resources for that particular process. That's the container deployment. Now, there is the potential that the container engine actually has to go talk to a registry and pull that container resource in. Again, the value of the lightweight model for containers, the just enough resource to actually run your process model, is that those containers can also be very small. We might be talking 100 kilobytes or maybe a megabyte in size for a small container. Now, containers can also grow very large. We've seen multi-gigabyte scale containers as well, and that seems to be the wrong direction for what most people want from containers, which is some of the speed aspect. But we have seen that as well. So it does go both ways. It's not like these are hard and fast rules, but these are sort of the general reason and perception behind why people do this. The second thing is, if we look at then a virtual machine, the best case scenario, even with virtual machines that are optimized for starting quickly, often we're still talking 5, 10, 15, 20 seconds for a fast VM. And in some cases, where we're really emulating a lot more of the hardware as well, we might see multiple minutes to start a virtual machine up. Now, virtual machines are usually pretty quick. Again, do I have to pull the image in for the first time? In which case, suddenly I might add many, many, many minutes, because often I'm talking at the gigabyte scale or larger as a small image for a virtual machine. And so that startup might be delayed as well by having to collect an image from some remote source. And if I still talk about physical machines often there's an additional set of overhead, which is that the physical machine, when it starts, it wants to do its own validation of the physical hardware, and that often can add minutes. I've seen some large memory systems take 15 to 20 minutes just to get through their BIOS process, let alone then getting an operating system loaded into that environment, which might require booting a micro operating system and then transporting that image over a network segment to actually get an image onto the disk, which then causes another restart, which might add additional minutes to the whole process. So hardware potentially is very slow, although there's some ways to speed that up. Virtual machines are faster, but have the potential to be still slow in their process. And then containers, sub-second launch. Well, that sub-second launch is one of the key value propositions, especially if I have the image locally, so I'm not constantly removing the image or putting it somewhere else. If I'm managing and manipulating my image locally initially, that sub-second aspect becomes very interesting from the development perspective, right? I can actually build my image locally, I can run my image locally, I can validate my image locally, and I can do that on my laptop. That same image can actually be potentially reused in production. I say potentially because you might want to add additional resources or services in production, but the idea behind the container development model, at least the way most people are doing that today, is to actually keep that restricted to actually managing those containers within or managing all those resources within the container. So deploy everything, have all of the resources that you're going to have in that container running, so that you don't have a delta between what you're developing against and what you're doing in production. That's one of the agile concepts that I think is very powerful and hopefully continues to become a major component of this. Another capability that's driving people towards this container concept is this idea of layered images. When you're actually manipulating an image, the Docker file, at least the Docker format of this, is to actually describe each major step of a process as an image layer, basically an extension that's being mapped on top of the base disk, the disk equivalent for the container, step by step. So if you do an apt-get install or yum install or apt-get install, in either case, if you actually install a service, let's say we're going to apt-get install Apache or yum install HTTPD. In either case, that becomes one layer within the image. Now, if I then change something later in the Docker file that doesn't actually impact that particular initial install, or I don't have a check to see if I have the latest version of something installed, it turns out that I won't normally touch that layer again if I make a change later in the Docker file. So for example, the last thing I would probably do is actually define my actual application, potentially pull that from a Git repository, for example. So pull the actual source code in and potentially run a compile step or some other post-processing step on bringing that data in and making it consistent and runnable. But if I actually then update my code, I'm not necessarily reinstalling Apache, reinstalling Fusion, for example, and then reinstalling my Ruby code. I'm just reinstalling my Ruby code and creating a new version of that image. That actually vastly simplifies the process of building out a service. Now, I can do this in the virtual machine space too. I can clone a virtual machine and then just update my code within the image. But unless I managed to clone my system before I installed my repository and did my post-processing steps, I might actually have some deltas between a clean system and my now dirtied system that I've updated or overwritten with code. And it's that cleaning process that is effectively part of this Docker layering service, because I've effectively built an intermediate set of snapshots into the environment for every stage of what I have in my Docker file. So again, a very powerful approach to managing this service. And I would say the last major thing that sort of forces people to stick with or potentially like the container service is this potential additional operational value. Now we're going to talk about more about this later, but one of the things that we're finding with the container operating environments is that they often include load balancing capabilities. So Docker in their latest release just included base level, container level load balancing as a part of their embedded resources. So something that you can just ask the system to do for you rather than actually having to specifically implement a load balancing container and then configure it for the containers that you've deployed behind it. The Kubernetes environment has done this for a while. Some of the others like the Fleet guys and Rancher guys are doing this as separate add-on services on top of the base platform. But that additional operational value is a very powerful component as well. So just to sort of reiterate, the container concept, we're really talking about processes and process containers. The virtual machine concept, we're talking about an operating system container. So when we're thinking about this as a developer looking to consume these resources, I think it becomes very clear that the less they have to consider the whole operating system and can just focus on their process and the resources needed to make their process run, the happier they likely are. So one of the real drivers behind this concept of containers is the agile development craze, sort of the DevOps resources that have come from that. And if we kind of look at the history here, we see things like Amazon Web Services changing how application developers consumed their infrastructure. Basically, the concept of infrastructure as code came out of the DevOps and Agile communities. The Agile guys wanted to be able to constantly develop and test and validate their codes. Every time they would write something, they'd like to be able to test that in a production equivalent system. That makes for good Agile development practice. At the same time as Amazon, about 10 years ago or so, released their web services interface for EC2, their elastic compute model, suddenly developers that used to have to deal with an IT department or somebody else to actually provide them with an operating system that they could run their code on, suddenly had the ability to ask for that to automatically be provisioned for them. Now, in doing so, they effectively took on the mantle of some of the operational complexities of managing operating systems, managing security within the operating system. They suddenly had to manage more of the network service, what ports were actually being allowed to get access to their virtual machines and things of that nature. But it gave them the ability to start modeling all of that as code, and so the infrastructure as code component came along. The container shift really sort of kicked this into high gear because suddenly the developers didn't have to wait potentially minutes to get their application and virtual machine up and running. They could just launch a container, which takes seconds, especially on a laptop. It suddenly becomes very fast. And the container shift also helped because the developers and operators of that development, the DevOps resources, suddenly realized they could effectively ignore most of the issues in the underlying OS. They would assume that gets handled by somebody else, which made their life easier. So I actually always talk about the fact that developers really don't like operations. DevOps is really a stepping stone for many developers. It's actually good for them to understand the infrastructure, but in the long run, they don't want to understand it. They don't want to deal with it. If they don't have to, they can focus on their application development. And from a general business perspective, this is actually a really good idea, is to get the developers to not have to deal with additional work. They can focus on features and functionality rather than on the operational complexities of the underlying resources that they had taken on. They took it on because it made their lives easier, but now containers potentially let them release or relinquish some of that control and get back to really focusing on the application, but still having the same kind of flexibility that they had experienced in the, yes, you need to manage the operating system component. So again, the developers really would prefer to reduce or limit the amount of operations that they have to do, and really just focus on those things that are operationally directly related to their application. So I've noticed that developers are willing to either implement load balancing or leverage load balancing and configure and have their application talk to a load balancer, basically make sure that the load balancer is talking to an active service rather than a non-active service. And actually, I think this is the kind of capability that's driving this growth in this concept of the serverless development resource and community. They're just focusing on the application again. Now, I think it's a joke because even a serverless application still runs on a server, still has to have somebody managing that server. But I think the thought behind it is that now the developers no longer have to think about servers. They're just thinking about how their applications are bundled and run and potentially scaled. So that's pretty powerful. Developers do, while they don't like the operational complexity of things, they certainly do like containers. And again, one application environment, one model, the simplification of the layering that comes along with things like the Docker image format, or the way that Docker set up the image format, I guess is a more accurate way of saying that, makes it easy to build an application in your test environment. Once you have your development and your test environment in sync, so you can do unit tests locally on the equivalent of a production target system, I can pass that same capability on. If I have a separate QA or systems validation and staging teams, I can pass that same image on, and we can use the same code, the same exact bundle every single time for all of the different phases of a release process. Now, again, my view of the world today is that these processes should all be automated, but being able to manage and manipulate these capabilities is really incredibly powerful. So the container model just sort of simplified the application development environment, removed some of the operational overhead that the developers were currently managing that they really didn't want to manage, and really lets everybody focus on the actual application that wants to be built. So overall, this is very powerful. The reality is that even though we're limiting the operations, we still have some operations that need to be accommodated. We can't avoid everything. One of the things that we can't avoid is basically dealing with application failures. The container model doesn't necessarily do anything other than try to restart the container. That's often a core part of the service. And an example of that is the Core OS, lightweight OS, basically a container-focused OS, actually uses the systemd process management, basically daemon management functionality to manage and maintain the containers that are deployed. So if a container dies, systemd learns that that process is no longer running and it tries to restart the process, basically relaunches the container. That's great if that's really what needs to be done, but something else still needs to potentially monitor and manage that process so that you don't end up with dead systems that think that they're doing the right thing. So we still have to operate our application and our application lifecycle, and manage failures gracefully and manage scale gracefully. Another thing is, of course, this concept of scale. So you could deploy a container that provides a load balancing functionality, but that's as complicated to manage as it would be if it was a separate virtual machine. And again, not something necessarily that really does much for your application except for providing that application level scale component that most people are looking for. Certainly there are load balancing concepts, basically more like routing concepts, application routing concepts that might be implemented as a load balancing like function, and those would not necessarily fall into this operations of the infrastructure category, would actually really be more operations of the application category. But still, being able to provide load balancing as a part of the container service is a very powerful thing that the operations team can enable, and some of those services do exactly that. And lastly, there are questions about managing interactions and how do I actually access these containers? Does everybody have sort of flat access to the environment? There still is operational complexity in managing and manipulating who has access to what resources at what point in time. There's also a question about security that I think still is being addressed. It's being addressed partially by ensuring that you have traceable images that you can build from, so you actually know the provenance of an image that you use. That's one piece of the puzzle, but there is also the concept of maybe dealing with security in a different way, rather than having everybody's container live within a shared container environment. Potentially containers could be deployed into container management nodes that are virtual machines themselves, so therefore segregated at the virtual machine level from other kernel level interactions, but still providing the container-based management interface for the end user operators. But it's not just containers that we're talking about, right? So this operations requirement really leads us down the path of considering the container management field. And so here we see things at the sort of the lowest level, sort of the CLI and API-based level, things like LXC with LXD. LXD is really a RESTful API on top of LXC, but it makes it potentially easier to consume, especially programmatically. And there are also additional tools that can tie into other systems level management tools, like there's the libvirt LXC plugin. Libvirt is a virtualization management library in the Linux space, and it's often used to manage virtual machines. Well, in this case, it's just pointing to an LXC container instead of a VM on KVM, for example, or QEMU. We also see container management from the folks at Docker, specifically, well, with their latest release, they've effectively integrated the Swarm components and made that operational enablement simpler. So basically the ability to turn on a cluster of Docker-based nodes in conjunction with Swarm is a pretty powerful extension. Well, we have Docker, LXC, and Kubernetes. So Docker and or LXC provide the container runtime management, so the individual container management resource, and Kubernetes provides a higher level management platform. Basically, the model with Kubernetes is this concept of a pod, which is effectively co-located container resources, which might be multiple containers. Those pods expose basically TCP or UDP ports to a service. The service then is a construct that basically tries to map those ports to publicly accessible resources, or at least security appropriate accessible resources, whether that be a specific network or an internal forwarding network, for example, to tie into VM running a database and containers running an application server. You could do that through some of the Kubernetes level management. And Docker is looking at that sort of management as well as a part of their overall tool sets. So this concept of management is that you're managing a bunch of different things. There's also the concept of doing the same sort of thing. Rather than using Kubernetes as the management layer, you could use the Mesos or Mesosphere tools, which is really a scheduling and resource management application, along with something like DCOS, which tries to provide a data center-wide view of a set of resources. Again, thinking about things like load balancing and scale up, scale down across an application suite rather than just across a single component. So another piece of the puzzle is, of course, the Docker Cloud, Rancher, DCOS, and CoreOS with Fleet kinds of capabilities. Basically, tools that sit even at a higher level, potentially looking at multiple clouds even. So you would have the Kubernetes project mapped into that as well. So really thinking about the tool set of managing virtual machine-based clouds, container-based clouds, and potentially even remote virtual or container or even physical resource clouds for that matter within that environment. And so we're talking about all these different management functions. And if we sort of bundle them all together, we can think of things like lifecycle management, so the management of the container from creation, image management, image download, image updates, systems updates, start, stop, pause sorts of functions, right? Managing all of those things potentially as a part of a system rather than as an individual container. The concept of managing and manipulating things for rolling upgrades. So maybe I have 100 containers deployed and I want to update them to a newer version. Rather than turning them all off and then turning on a new 100 set of containers, I might actually want to roll into that 100 new services and slowly trickle new data into those services over time, basically scheduling, load balancing, and container updates at the same time. Very powerful functions that exist within that sort of environment. Managing and manipulating scheduling of resources in and of itself is another task that's often beyond what an individual container manager engine can do, but is part of the operations management resources. And then network and network service, dealing with potential multiple layers of overlays or mapping a physical resource into a virtual resource, at least at a local level, is another part of the operations component. And then storage as well. I might actually have persistent storage that I need within the container world. Given that containers are often considered these ephemeral resources, being able to map storage and provide persistence is actually an important aspect for some application environments. In reality, I think about this, and I think that infrastructure as a service type offerings, those services that manage a lot of the baseline management services, has the exact same set of requirements. Hey, I need to spin a virtual machine up or a physical machine up. It needs to live for a while. Eventually, I need to sort of migrate to a newer version. I want to roll the upgrade out to my remote resources. I have to schedule resources, etc. All those functions look a lot like the infrastructure as a service offerings, but now I'm applying that to containers. Well, one of the interesting things is, what if I map the two together? So again, my history is that I've done a lot of work with OpenStack over the last 5 years, and as such, I want to talk about this relative to OpenStack. But the reality is that this applies to any of the infrastructure as a service offerings. I think in both cases there's the potential that these things sort of sit together. So if we think about OpenStack and containers, or any cloud service in containers, there are really sort of two principal models for running containers on an infrastructure service. And there's also the concept of potentially running the infrastructure service management layer on containers as well. So a little sort of chicken and egg kind of a question that potentially comes up. When we talk about running containers, really we're looking at using the virtual machine or potentially even physical infrastructure machines like bare metal management machines to enable a container-based environment. Now that might be deploy a Linux OS and Docker, or a Linux OS and run C on top of that base OS. Or it might be the deployment of a container OS. So one of the common ones is something like CoreOS, which provides just the barest of Linux kernel and basic services, basic terminal services, so that you can actually get in and configure the environment directly if you have to. But the intention of something like CoreOS is that actually it gets configured and provisioned programmatically. So when it comes online, it knows what it's supposed to be a part of. It knows what resources it's supposed to determine and capture and potentially deploy locally. So managing the deployment of those resources is always a question. It's that, how do I get this cluster up and running, and then how do I manage the underlying infrastructure of the cluster? Core part of that question. We're also seeing people talk about managing containers directly from infrastructure as a service like systems models. Again, if I have all those sorts of capabilities, enabling load balancing, managing lifecycle of resources, why do I need yet another interface like the Docker interface to do that? And so there are some folks in the OpenStack community that are actually trying to rewrite that aspect as well. I find that less interesting myself. I figure that there are enough good models that seem to be functional for most developers' requirements that we don't actually have to do that. And then there's the question of, when you're running a container, for example, in an OpenStack environment, there's still the question of what you're actually layering on top of that. But it's interesting because those questions can be handled potentially on a tenant by tenant basis. So in one case, a tenant might want an LXC, LXD based environment. Another one might want a Docker based environment. Another one might want Kubernetes on top of run C or something along those lines to actually implement the actual container management functionality. And the nice thing about an infrastructure service is that I can deploy a physical or virtual machine and have it automatically provision one of those resource models. So a pretty powerful approach to handling a lot of this. Another thing that I get out of an infrastructure service is that I can actually build these deployments on a tenant by tenant basis. Now, tenant or project is usually the way it gets described, at least in the OpenStack space. Gives me the ability to put different networks into the service, to attach potentially different external network services and functions, attach storage functions, share different backends, or broker the backend by basically exposing the OpenStack resources into the container system space. And this capability really helps manage the underlying infrastructure that is needed to run a container environment, but isn't necessarily ever actually exposed to the end users within that solution. Another capability would be the scheduling capability, basically dealing with container management and scheduling resources, making sure that those resources are actually being mapped to an appropriate distributed set. The last thing that I want to do is spin up 4 container nodes to run my Kubernetes masters and minions and find that they're all on the same physical server, even though I have 4 or 8 physical servers available to actually deploy those resources onto. So being able to define affinity or anti-affinity is a core part of what the scheduling can actually enable. There are some gaps though. Currently, there really are no interactions between the container-based scheduling resources. So, for example, Kubernetes or Docker Swarm type environment does have at least some concept of scheduling resources across a cluster of systems, or just deploying containers across a cluster of systems. But there's no interaction between that level of scheduler and the underlying infrastructure as a service scheduler, e.g. As an example would be the Nova scheduler, or one of those resources schedulers that's trying to figure out where to actually place the virtual machines. So that just means that you actually still have to go and check and make sure that the virtual machine is being distributed onto a physical resource that still has the performance you need to actually implement the actual function the container was supposed to provide. This scheduling issue is really no different than any other cloud application, though. If we think of the container environment as a cloud application, then there are many of these sorts of things that we would actually have to manage just in terms of deploying our own application. So deploying containers this way, really not such a big deal. And besides which, at least within the OpenStack and Amazon and GCE spaces, there are already templates for managing and manipulating and deploying a container environment. So we can just reuse those. We don't actually have to try to build a lot of this stuff from scratch. Now there is still the question of, what is the right interface to all of this? The OpenStack community has spent a lot of time trying to provide a consistent and while slowly changing and version managed set of APIs to talk to the environment. The same is actually true for Docker and Kubernetes. They're both also trying to keep to a consistent model for communicating with their overall capabilities. So we could actually look at saying that those interactions really want to consider basically using something like the OpenStack interfaces and OpenStack management layer to actually manage one environment for everybody. So we just provide containers as a service, but with one model, a Kubernetes model, a Docker model, etc. One of the nice things about this is that from an operational perspective, I have consistency. It's not like I have to try to help somebody debug their Docker-based environment and somebody else then go manage and debug their Kubernetes-based environment, and a third guy who's decided to run Red Hat Atomic with LXC as their model for managing containers. You have one model that's consistent for everybody. There are some issues with that centralized model, and one of the biggest is the potential security implication. When you have 2 containers from different tenants on the same physical machine, there is a potential, even though it's very remote as far as I can tell, I'm not sure anybody has ever actually hacked, at least in a live environment, between containers, but you are sharing a kernel interface. So the actual running kernel that everybody potentially has to talk to consume memory resources, etc., is shared across potentially multiple tenants, unless you actually have enabled scheduling to have visibility all the way down to the physical host, or at least the virtualized host, so that the scheduler can actually keep tenants in different environments and limit that potential security implication. We could also do this management on a per tenant basis, and there are a number of tools to actually help with that, at least in the OpenStack community space. And certainly there are templates within Amazon and templates within the Google Compute environment to deploy scalable, stable environments. There's also no reason why a tenant couldn't decide to deploy container resources themselves on top of an infrastructure service, just by either describing a script or following a set of manual steps to turn on a Docker-based environment, for example. So the only issue with that really is that once again you've made operations managers infrastructure managers, and often those operations managers are also your developers, which means that your DevOps model that was so nice and clean because I just have to deal with a container interface and really only focus on my application and its core components, Now I actually have to manage the virtual machines and the actual container engine itself within that environment, which again can be done programmatically. That's one of the benefits of the Docker environment, but does add that complexity and that potential overhead on top of the DevOps engineer's head. At the same time, you could leverage one of the automation tools to at least reduce the overhead there, but it doesn't eliminate it. So you still end up with some management components. Now, as I was mentioning earlier, one of the things you can consider is using OpenStack not only as an infrastructure piece, but potentially as a resource on top. So people might want virtual machine management, would like to have an OpenStack environment to do that virtual machine management. Well, here's a way to either run your system as a service or provide OpenStack as a container-based application that your end users can then use to potentially talk to a set of VM-based resources that might actually be in another OpenStack environment. So a little bit, again, of Mobius strip-like functionalities. One of the nice things about potentially deploying a service like OpenStack within a container environment, especially a container management environment, again, a Kubernetes, a Docker with the embedded swarm capabilities in its latest release, or even on top of something like CoreOS, is the concept that there's embedded load balancing for some of these service-based constructs. So specifically the latest version of Docker and Kubernetes both support load balancing service embedded into their resources. So as I scale a resource, I actually can load balance the front end access into that resource, both embedded in the container environment and also possibly through a third-party load balancer plugin. Another thing is managing and manipulating storage. Since most storage these days is network service attached, whether SAN or directly via Ethernet, often you're mapping storage to a resource to make it available to that resource. So mapping storage to VM is fairly common. Mapping storage to a container is just as valid, although potentially a little less common. But then if I need to add additional storage or want to upgrade the storage environment or things of that nature, you can actually use the container-based resources to manage and manipulate some of those capabilities and pass that value into the OpenStack or infrastructure as a service sort of system space on top of that. Also, you can help manage and manipulate the infrastructure middleware. Some of that may be more appropriate as VMs than as containers, but for the most part, you can actually deploy those resources as containers, provide for lighter weight service deployment and a faster deployment service at the same time. But in either case, there is this constant chicken versus egg question. Do you deploy OpenStack and use that to deploy your containers, which then you deploy the production OpenStack service on top of? Do you just get a container environment up and running and then deploy OpenStack as a container middleware that can talk to other hardware as a part of that? There still are questions, and it really depends on where your team is strongest and what they're really trying to accomplish. So in either case, let's just use Kubernetes and OpenStack as an example. In either case, I need to have hardware. I need to get some form of base operating system onto it, and I need to then deploy additional resources. There are some models that look at effectively a build service, which might actually be a standalone small OpenStack environment, potentially with something like the Ironic driver enabled so that it can actually go out and build physical infrastructure for you. On top of which you could, even at that initial boot, just load a Kubernetes or Docker environment. So once that environment is bootstrapped, it's also possible to then migrate that boot management process into the cloud, into that container cloud as a container, which means that potentially that container can effectively chase its tail and hopefully not kill itself off on the physical machine that it suddenly finds itself living on as it migrates around the space. There is actually a project that currently focuses on taking all of the OpenStack services and creating a container per individual process. So, for example, in the Nova compute management space, there are processes for scheduling, processes for the API endpoints, processes that are just the actual scheduling decision-making process, not just the general scheduler, but actually the sort of the engine that does the comparison for that. There's a component called the conductor, which is a tool that's being used to help scale out the compute resource interactions with the core Nova controllers. All of those things can be containerized, can be put into containers and then deployed into a container management environment. again, if I have a container management environment like a Kubernetes or a Docker Swarm, I can potentially even load balance those resources that I deploy. So rather than deploying one container for Nova, I might deploy 3. Rather than having one database, I might have 3, etc., to provide additional resiliency. And potentially, if I have enough systems to actually make this meaningful, I can use the environment now, the container-based environment, to support rolling upgrades, because I can upgrade to a newer container version, and if it fails, I can downgrade back to the previous version, potentially much more effectively than a virtual machine, if for no other reason than turning on and turning off a container is effectively instantaneous, whereas doing that with a virtual machine might actually take physical wall time, like actual minutes to do. So in review, containers, really we're talking about segregated processes, and that is in contrast to virtual machines, which are really segregated operating systems. The nice thing about containers is that in general they abstract a lot of the operations model that developers really don't want to have to deal with, or like giving up for the most part, dealing with base operating system updates and upgrades, patches, etc. Just focusing instead on making sure that they have the right set of libraries that have been tested end to end with their particular application, making for some real power. At the same time, we also realize that while containers provide a lot of value from a developer perspective, there is still an operational complexity that needs to be addressed. How do we scale the container infrastructure? How do we make sure that the scheduling is in some way integrated between the two environments? Actually, when we talk about scheduling, we could also talk about network and storage, etc. All these tools have to still be there to support the container space, but manage it at an infrastructure services space. And then of course, then there's the question of security. Is it okay to have multiple tenants or multiple projects sharing one potential kernel systems interface? Or would it be more appropriate, again, this is really sort of system specific or customer specific, but would it be more appropriate to actually have that security boundary managed within a container that is contained in a virtual machine on a per project or tenant basis? So again, questions that can be looked at, that there are no right answers. There are answers that are appropriate or more appropriate for specific environments. But I always look at this and I say, to me, given what infrastructure as a service can do, why wouldn't you run your container environment on top of an infrastructure service? And that's really the value of what we're talking about. So at this point, I'm happy to take some Q&A. I don't know if there are any questions currently, but if there are, I'll take them. And with that, I want to thank you for watching this webcast. Hopefully you'll join us next time when we talk about some of the different environments that people find themselves looking at in terms of making the decision about what sorts of containers they would like to deploy. This has been Robert Starmer, and I'm looking forward to the next session. Thanks so much.